Math 1314, section IC1, spring 2022, Tyler Junior College. Homework 9.1/9.2, inverse functions, exponential functions. Video 4, graphing exponential functions via transformations. Not sure what happened there. All right, in the previous video, we introduced exponential functions and looked at their graphs from a plotting points perspective and extracted some properties from them. Namely, it has a y-intercept at 1, no x-intercept, strictly increasing or decreasing depending upon if the base is greater than 1 or less than 1, and has a horizontal asymptote on the x-axis, but only on half of the graph, depending if the graph is increasing, asymptote on the left, or decreasing, asymptote on the right. The domain of both of them was all real numbers, and the range for both of them was 0 to infinity, not including 0. And they each had a base point at 1, b. But we can also graph exponential functions by using what are called transformations. Transformations are taking a previously existing graph and doing one of three things to it: moving it around, flipping it one of two ways, and stretching it in one of two directions. We're only going to focus on the moving graphs around and flipping them one of two ways. We're not going to focus on the stretching. All right, so we're going to do this by taking something that we know and trying to figure out the impact of adding or throwing some extra numbers into the function. So we're going to start with an original function of f of x equals 2 to the x power. Now, I've already got this graph pulled up in Desmo, so I'm going to remind you what it looks like. It does have a horizontal asymptote at y equals 0, aka the x-axis. Let's make that asymptote dotted because it's an asymptote and it just looks more like one if we do that. The graph is strictly increasing from left to right. It's got a y-intercept at 0, 1. The base point is at 1, 2, because the base of this function is 2, as you can see over here. There's an asymptote on the left half. And by the way, it looks like it crosses the x-axis. I promise you it does not, because if we were to kind of go over here somewhere and just zoom in ridiculously large, we would see that if we get close enough, there's a gap between the graph and the asymptote. And it doesn't matter how far to the left we go, there will always be a gap. It's just an illusion, excuse me, because the size of the pixel, the size of the dot drawing the graph over here is bigger than the actual distance between the graph and the asymptote. But we're going to see what happens when we throw some extra numbers in here. Now, we could discuss this analytically, but we're going to take the evidence-based approach, meaning that we're just going to graph these and we're going to see what happens to the graph. All right, we're going to start by adding, and I'm going to be using the number 3 in most of these just because I picked a number. Let's start by adding 3 to the function. Let's think about this real quick before we throw in the graph. If I throw a +3, then what that will do to my outputs is they'll make them 3 greater than they used to be. Well, the outputs are the y. So if my y's are 3 more than they used to be, where do you think the graph is going to move? Well, if the y's are 3 greater than they used to be, then the graph ought to move up 3. And if we hit a +3 on the end, now we have evidence that that happened, because this point, the y-intercept moved up 3. And notice that this base point, which is not showing unless I click on it, also moved up 3. So it seems like the effect of adding a 3 on the end of the function moved the graph of the function up 3. And that's exactly what it does. So the effect of adding a 3 at the end, adding a number at the end, moves the graph up. Adding a number at the end moves the graph up. And then there's a reason I said at the end. If you glance down a couple of more, you'll see these are actually up with the exponent. But adding a number at the end moves the graph up. Now, what do you think subtracting a number at the end will do? Well, again, the output is the y value. And this function says, before I give you your y value, I'm going to lower it by 3. So what do you think that will do to the graph? If you said move the graph down by 3, well, watch the black graph. It is down by 3. The y-intercept went from 0, 1 to 0, -2, and the base point went from 1, 2 to 1, -1. And in fact, I'm going to have this automatically plot the base point every time we change this, and I might as well keep track of the y-intercept as well. Just using some Desmos goodness here to do all this. And let's go a little more color coding, if we will. We'll keep everything on the original graph black, including the original black, and we'll have everything on the new graph red. So red and red. Now, it is worth mentioning that as this graph moves up and down, so moves the asymptote, because this asymptote would have to move down to -3 in order to be the asymptote for the newly moved graph. Right, and also notice that the distance between these over here doesn't look like much, it looks like a lot. And as we move to the right, it looks like there is no distance in between. That's because, relatively speaking, these numbers are growing so fast. A distance of 3 between them is insignificant. It's like if you're driving 10 miles an hour, then 100 feet looks like 100 feet. But if you drive 100 miles an hour, 100 feet goes by in a flash. I don't think that analogy worked as well as I thought it would, so just pretend I didn't say it. All right, so we now know what happens when we subtract a number, and that was not supposed to be red, but you know what? I like it that way, so we'll leave it that way. Now, what happens if we subtract a number? Well, subtracting, I'm still not sure how that turned red. Subtracting a number at the end moves the graph down. Let's put that in red, because I think it looks good that way. All right, so what do you think will happen if we actually add a number up on the X? I'll give you a hint. It won't move the graph up or down. Oh, then I must move it left or right. And since it's a +3, it probably moves it to the right. Let's find out. Let's go back to the home screen here so we can see the two graphs. Let's go to this function, take the -3 off of here, and we'll do +3 up here on the X, up on the X. Okay, you're going to make me put parentheses around it just so I can say +3 up on the X. I can do that. I'm going to turn off these points also. I thought I turned them off. I guess it's going to show me the y-intercept. Oh, it's still labeling them. Never mind. Okay. Whoa, where'd the graph go? Did it move to the right? It did not seem to. It seems like it moved to the left. Well, if it moved to the left, then this point would be here. So is that the correct point? It seems like it. The y-intercept moved to the left 3. What about the base point? The base point moved to the left 3. Well, if it did, it would be at -2, 2, and it is. So it looks like adding 3 on the X actually caused the graph to move to the left. I can illustrate this by putting a slider in the function. In other words, I've got some number being added to make the new function. Right now, it thinks that number is 0. Let's move that up to 3 and watch the red graph as I move this up to 3. The red graph is, well, it's a little bit deceptive. I need to change something here, folks. 1 second. We're going to put a C here so that we can keep track of the base points and the intercept. So I think I've got this set up properly. Let's try to, yep, that'll work. All right, so as I take the number being added to the X and increase it to 3, everything is moving to the left. To the left 3. Now the asymptote moved to the left 3, but it's a horizontal line, so you can't tell that it moved. Net result is, let's see if we can edit this so that it works. Text, please. So that it works for this. We didn't add a number at the end. We adding a number to the X moves the graph left. In fact, I want to go back up in here and put in all caps where we put these numbers at the end. Subtracting a number at the end. Come on. Moves the graph down. Adding a number to the X moves the graph left. So what do you think subtracting a number to the X is going to do? In other words, when we subtract a number, let's get rid of this for a second. When we are subtracting a number to the X, where do you think it's going to move the graph? Well, it can't move it to the left, and it can't move it up or down. Well, that kind of only leaves one direction if we're only moving north, south, east, and west. Seems like it's going to move it to the right, which seems completely counterintuitive. Why would a negative move something to the right? Well, let's go check it out. Let's look for evidence. So we're going to slide this back down to 0, and I'm going to change this to minus. And now I am going to, that's what I figured would happen. I'm just going to get rid of these points because I can't fix them quickly. Oops, I wanted the slider come back. All right, so right now it says x minus c, and right now c is 0, so it's like it's not there. But let's raise this up to 3 and see where the graph moves. It is indeed moving to the right. Our intercept did move to the point 3, 1. And our base point, if we moved it 3 to the right, is at 4, 2. So it did move everything to the right, which means we can now take the question mark off here. Subtracting to a number to the x moves the graph to the right. The left and right movements seem counterintuitive. You think plus 3 would move to the right, but it moves to the left, and you think minus 3 would move to the left, but it moves to the right. Up and down is intuitive. Left and right is opposite of what you expect. Now, what happens if we throw a negative in front of these things? Well, let's think about it. The second function says, I'm going to give you the y value, but before I give it to you, I'm going to stick a negative on it. So instead of going up, it would go down. So all the points that are up will now be below, and the whole graph ought to get flipped upside down. Let's see if that comes to fruition. All right, let's take off all this slider stuff. We don't need it anymore. Just put an X up there. And let's stick a negative in front of the function. And sure enough, it turned it completely upside down. Took the mirror image across the x-axis. This is what's known as a reflection, like in a mirror. So putting a negative in front, hold on. A negative in front of the function reflects the graph across the x-axis. Let me put x-axis in caps because you can probably figure out what's going to happen in the last one. A negative in front of the function. We'll put function in caps. A negative in front of the function reflects the graph across the x-axis. So what do you think is going to happen down here? Well, it's not in front of the function. It's in front of the x. And it's not going to reflect it across the x-axis, but it's going to reflect it across the y-axis. And we can get evidence of that by going into Desmos, taking the negative off and from in front, and we're going to stick it right in front of the x. So I want you to picture this graph spinning across the x-axis, the y-axis, and it would look like that. Did you catch it? I can kind of make it have this 3D effect, but you'll have to use a little bit of imagination. Give me 1 second. I got to set this slider up. Okay. Let's take this slider. No, I want a slider, please. Thank you. All right. So I want you to watch that red graph, and I want you to imagine it spinning in 3 dimensions. So coming off the screen and spinning to the other side. Watch it. Now, it may have been kind of hard to see it. It just looks like it's bending up and down like this. But if this were in 3 dimensions, it's almost like this is spinning. Actually, you know what? No, it's not, because at no point would our perspective look like that. So you know what? Forget what I just said, except that sticking a negative on the x will reflect the graph across the y-axis. I was thinking something cute and clever, and I was incorrect. Here are the 6 things you need to know. Now, let's apply them to one graph real quick and wrap up this video. We're going to sketch the graph f of x equals -3, all raised to the x plus 2 power, and then -1 at the end. Now, this is obviously going from one movement to a lot of things, but I think this is something that we can handle if I can make my name disappear. All right, so we're going to focus on what the original function would have been, and then the changes invoked by all of the additions. The original function would have been f of x equals 3 to the x. which I can tell because the base of this is x. If we stripped off the minus in front, the +2 on the x and the -1 at the end, this would be our original function. And I know a lot about this original function. I know it has a y-intercept at 1. I know its base point would be 1, 3. Its y-intercept would be 0, 1. I'm erasing the 1 because I want to put the ordered pair 0, 1 here. I know it has a horizontal asymptote on the x-axis. Let's make that blue, something a little more contrasting. I know it has a horizontal asymptote on the x-axis, and I know that this graph is increasing. So it would start low, get high. There's a joke in there somewhere. But what changes will all of the additions to the function create, starting with the negative in front? What will the negative in front do? Well, a negative in front will cause it to reflect across the x-axis. So this graph's going to have to get flipped upside down at some point. What will the +2 do on the x? Now, this is the one where you have to be careful, because you would think if it moves left or right that would invoke a movement to the right, but adding a 2 on the x actually causes it to move to the left too. And what does a -1 at the end do? Well, a -1 at the end causes it to move down 1. So to get the new graph from the original, we have to pull off all 3 of these moves. We have to reflect, move left 2, and down 1. The question is, in what order do we do them? In general, you do your reflections first and then your movements second. So let's start with the reflection and then we'll move everything. In order to do this, we're going to try to keep track of the base point, the y-intercept, and the asymptote. Excuse me. So let us do all of that. We're going to make a little table here. We're going to say y-intercept. Let me take the font size up. We're going to do y-intercept. We're going to do base point, and we're going to do the horizontal asymptote. All right, so let's start with, 1 second, I'm getting this formatted a certain way. Let's start with the original. Okay. So the original, the y-intercept was 0, 1. The base point was 1, 3, and the horizontal asymptote is at y = 0. Now, if we do the reflection across the x-axis, and you see I'm kind of spacing this out as I go. If we do the reflection across the x-axis, everything on the top flips down to the bottom. That means everybody's y becomes negative. So the y-intercept flips down to -1. The base point flips down to -3, but the horizontal asymptote will stay on the x-axis. It's serving as the mirror over which we're reflecting. So our horizontal asymptote is still y = 0. Okay. I knew these negatives were going to create a little bit of an issue, but I think it's something we can handle. All right, so we do the reflection. Now let's do the left 2. Now think about this. When you move a point to the left 2 on your number line, its x goes down by 2. So we have to take each of these points and lower its x by 2 to move the point to the left 2. Well, on the y-intercept, 0 - 2 is -2, but we're not changing the y because we're just moving to the left. And on the base point, which is at 1, -3, if it moves to the left 2, we have to subtract 2 from the x. 1 - 2 is -1. Y doesn't change. Horizontal asymptote is still at y = 0. Told you I was going to have to format this as we go. Not a problem. All right, and now we have to do the down 1. Now, what does moving a point down 1 do to its coordinates? Its x and its y coordinates. Well, moving a point down 1 would lower the y by 1, so we have to subtract 1 from each y coordinate. And the y-intercept, which is now at -2, 1, if I lower it by 1, it will be at -2, -2. The base point, which is currently at -1, -3, will get lowered by 1. And so the y coordinate will go down by 1. So instead of being down 3, it's now down 4. Now, I forgot to mention in the previous move what happens to the horizontal asymptote. Our asymptote was on the x-axis at y equals 0. When we move it left or right, it's still sitting on the x-axis, so it hasn't changed yet. Flipping the graph upside down, moving it left and right does not change the horizontal asymptote, but moving it down does. If the asymptote is on the x-axis and we move it down 1, it's no longer at y equals 0, it's at y equals -1. All right, so let's take this to the next page, take all this information and use it to sketch this graph. I know what some of you are thinking. I'll just put it in a calculator and get the graph, but we've had this discussion before. This is about thinking, being able to solve problems analytically without just saying, look, I pushed buttons on a graph and got an answer. Hurt. Okay. All right, let's think about where we need to put an X and a Y axis. Looking at all of our points, our X's, we're on the bottom row. This is our final result right here. I wanted that to be red, but that's okay. Our X's are all negative, our Y's are all negative, everything's negative. We need room below the X-axis, which makes sense because we turned everything upside down. So as we sketch this graph, we're not going to need any room above the X-axis. We will need room below it though. Now our X's of concern are at -2 and -1. So we'll just go back to -1 and -2. Our Y's of concern, looking at the 2 points in the horizontal asymptote, are -1, -2, and -4. -1, -2, and then down to -4. Let's start with the horizontal asymptote, which is at y equals -1. So we'll draw a horizontal asymptote through -1. I'd normally draw it dashed, but I can't draw a dashed line quickly using the tools in this word processor. Our y-intercept has now moved to the point -2, -2. So let's drop a heart there at -2, -2. And our base point has now moved to -1, -4, which is here. And if we connect them and remember that the horizontal asymptote is on the left, then we get a graph that looks a little something like this. Now, there is a new y-intercept, and we could locate it, but I can tell that it's way down there. In fact, I'll just go back and tell you what it is. If we put 0 in for the x on the function, 0 plus 2 is 2, 3 squared is 9. Put a negative in front to get -9, then subtract 1 to get -10. Our y-intercept is way down there at -10. I'm not going to bother finding it, but let's go to Desmos and just see if our graph is reasonably close. Desmos, please. Let's take all this out. Hasta la vista. All right, let's start by sketching where we think the horizontal asymptote is at y equals -1. Let's see, we'll make it look like an asymptote by making it dashed, and we'll make it red just because. And now let's just type our function. I forget it was g of x or f of x, but the name of the function is irrelevant. It was -3x to the, no, -3 exponent x, I forgot what it was. +2 in the exponent, then -1 afterwards. Okay, +2 in the exponent, -1 afterwards. +2 in the exponent, +2 in the exponent. Let's go ahead and put the -1. This is one big flaw of Desmos. You want to put more in an x than an exponent, you got to use parentheses. +2 in the exponent. And does this kind of look like what we drew? Very much so. Let's plot our 2 points that we kept track of, -2, -2, and -1, -4. -2, -2, yep. And -1, -4. Yep. Everything we predicted came to be. It's almost like we're be able to see the future. Now, all we did was analyze the function for all the information it was willing to tell us, put all that information together, drew a graph, and boom, just like that, draw the graph without technology. Technology came in and said, yep, that's what we said the graph was. And we were like, yeah, we kind of already knew that.